Okay, let's dive right into this masterclass on experimental physics. I see two types of students taking these Cambridge IGCSE past papers. First, there's Alex. Alex is the kind of student who just overloads every single answer with raw physics facts, dumping textbook knowledge onto the page, but completely forgets to actually analyze the experiment in front of them. And then, on the other end of the spectrum, we have Sam. Sam rushes through the paper, completely missing the specific command words the examiner is looking for and losing easy marks. Well, today on this explainer, we are putting an end to those flawed approaches. We aren't just looking for right answers, we're decoding the actual methodology to show you exactly how to think and act like a precision scientist. We're going to transform those red pen marks into green check marks.
Take a look at this seemingly small syllabus update. Historically, students use 10 newtons per kilogram for the acceleration of free fall because, honestly, it's just an easier number to multiply. But the standard has shifted to a much more precise 9.8. Now, you might be wondering, why does this even matter? Well, it proves a fundamental rule of experimental physics. Absolute precision and strict parameters matter. Examiners are specifically testing your ability to read the warning signs and follow the rules of the environment you're testing in. If a question gives you a specific parameter, you use it. Period. Missing these tiny details is exactly how students like Sam lose an entire grade boundary.
So, to help you avoid those exact pitfalls and truly understand the scientific method, we're going to build your practical toolkit across 4 crucial areas today. Number 1, measurement precision. Number 2, designing investigations. Number 3, analyzing data. And number 4, proving reliability.
Let's start with Section 1, measurement precision. Small errors, big impacts. But hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's get into the lab.
Okay, so if your foundational data is flawed, your entire experiment just collapses, like a house of cards. Take the classic pendulum experiment. The very first thing we absolutely must understand is the period. The period is the time taken for one complete uninterrupted oscillation. That means a full swing out and a full swing back to the exact starting position. It's the whole shebang. But measuring this accurately in a real lab setting is way trickier than it sounds. Imagine you're standing at the lab bench. Even something as simple as measuring the 50-centimeter length of the string to the center of the pendulum bob requires immense care. You have to use a set square perfectly at right angles to your ruler just to avoid a parallax error. If you just eyeball it, boom, you've instantly lost marks.
Now, here is where we see the difference between a rookie and a pro. Why on earth do we measure 20 swings instead of just timing one? Look at the comparison on the screen. If you try to time a single swing, the simple act of your thumb hitting that stopwatch button takes about 0.2 seconds. That human reaction time accounts for a massive, unacceptable percentage of the total time of one swing. It's a huge margin of error. But by timing 20 complete oscillations and then dividing that total time by 20, you drastically shrink the impact of your reaction time. It's a brilliant, incredibly simple technique to isolate the true period, and it's exactly the kind of methodological thinking that examiners are desperately looking for.
And this absolute need for precision translates directly into calculating complex properties. In one specific past paper experiment, students were asked to determine the density of water using a cheap, simple plastic cup. By carefully tracing the rim and the base to find an average diameter, and then measuring the vertical height, those raw numbers plug directly into this equation. Volume equals 0.785 times the diameter squared times the height. Notice how the diameter is squared in that formula? That means if you were off by just a couple of millimeters because you didn't measure straight across the center of the cup, that tiny error gets mathematically squared. It blows up. It makes precision absolutely paramount before you even think about putting that water on a balance.
Moving right along to Section 2, designing investigations. This is all about controlling the chaos.
All right, it's time for an interactive challenge. Imagine you're handed a ramp, a toy truck, some wooden blocks, and a selection of heavy metal masses. Your objective is simple. Does the toy truck's mass actually affect its stopping distance on a horizontal floor? I'm going to give you a mental 60-second timer here. How would you practically set this up in a lab to prove it without a single shadow of a doubt? How do you ensure the examiner has absolutely no reason to deduct marks from your method?
Well, to get accurate results, you can't just load up the truck with weights and push it down the ramp randomly. That's a classic Alex move. Lots of enthusiasm, zero control. You must rigorously control the key variables listed right here. The wooden blocks must maintain the exact same ramp height for every single trial. The truck must be released from the exact same point on the ramp every single time, and critically, you have to release it without applying any pushing force, just let gravity do the work. And the surface material of the floor, it has to be identical. You can't roll it on carpet once and then tile the next time. You have to control the chaos, ensuring the only thing changing, your independent variable, is the mass of the truck itself.
Now we're entering Section 3, Analyzing Data. This is where we find the story hidden in the numbers. But listen, stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, let's get back to the data.
Once you've actually gathered your readings, you have to extract the truth from the data. Take a quick look at this cooling water experiment table. This is a data scan challenge for you. We are comparing the cooling rates of 200 cubic centimeters of hot water against 100 cubic centimeters. By tracking the temperature drop at exact 30-second intervals, clear thermal trends start to jump out at you. A perfectly organized table visually lines up the variables side by side so your brain, and more importantly, the examiner's brain, can instantly compare the rates of change.
But to actually prove those trends and absolutely lock in those analysis marks, you need to bring in the math. We use this incredibly powerful formula. By isolating the temperatures at 0 seconds and at 90 seconds, you can calculate the exact average rate of cooling over that specific block of time. You just subtract the final temperature at 90 seconds from the initial starting temperature and then divide that difference by the 90 seconds that just passed. This brilliant logical step transforms raw, messy temperature readings into a specific, mathematically comparable metric. It takes you from just guessing, oh, it looks like it's cooling faster, to stating, it cools exactly this many degrees per second.
And when we pivot over from thermodynamics to electrical circuits, this single, beautiful equation becomes your master key. Resistance equals voltage divided by current, or R equals V over I. Whether you are testing the resistance of different wire materials or analyzing the brightness of different lamps in a circuit, manipulating this formula allows you to analyze physical constraints purely based on what your ammeter and voltmeter are telling you. It's the ultimate tool for cracking circuit behavior, and you should literally have it memorized like your own name.
Finally, we've arrived at Section 4, Proving Reliability, or, in other words, trusting your results.
Look, anyone can run an experiment once, get some numbers, and call it a day. But verifying that your data isn't just a random fluke, that is what separates amateur work from rigorous, top-tier science. Take the classic optics experiment with a plane mirror. You guarantee reliability by strictly following these geometric steps. First, drawing a parallel line exactly 10 centimeters away. Next, establishing a perfectly perpendicular normal line. Then setting the mirror to an exact angle using a protractor, and finally, marking the center of the reflected light ray with a sharp, precise cross. You can't use thick pencil lines and you can't just guess. You have to repeat the entire procedure multiple times to ensure the law of reflection holds perfectly true every single time.
Also, notice how checking reliability sometimes requires entirely changing your physical setup. In our circuit experiment, we start with the lamps connected in a series line to measure the total combined voltage. But to truly test the components and verify your data, you must physically unscrew the wires and rearrange the entire circuit into a parallel configuration. This allows you to isolate the ammeter to measure the current for just one specific lamp. Testing your hypothesis from multiple structural angles is the ultimate proof that your findings are robust, reliable, and mathematically sound.
So I'm going to leave you with this final, vital thought straight from the most difficult exam papers themselves. A true physicist always questions their own work. Even if you did absolutely everything perfectly, what hidden inaccuracy is lurking in your setup? Is it heat escaping from the top of an uncovered beaker? Is it a tiny kink in your resistance wire? Always ask yourself how you can prove your results are airtight. Think critically about your own methods, and you won't just pass the exam, you'll master the art of science. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCS to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCS and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.